Hello everyone. Welcome back to the course of data structures using C. This video is brought to you by Newton's group of institutions Macherla. This is Aravind Yegireddy from the Department of Computer Science and Engineering. Now let us see what is called as a max heap. So before going into what is heap sort, let us discuss what is max heap. As we know that a heap sort is an comparison based sorting technique which works based on the binary heap data structure, and it is similar to the selection sort where we first find the maximum element and place the maximum element at the end, and we repeat the same process for the remaining elements. So now let us see what is a binary heap. So let us first define a complete binary tree. As we know that a complete binary tree is a binary tree in which every level except possibly the last is completely filled, and all the nodes are as far left as possible. So we have to come from the left to right order. So a binary heap is a complete binary tree where the items are going to get sorted in a special order such that the values in the parent is of the parent is either greater than or smaller than the values of its two child nodes. Here the first one, that is greater than the 4 more, is called as max heap. That is the parent node is greater than the values in its two children nodes. And the later one is called the min heap. That is the parent node is smaller than the values in its two children nodes. So here we have two types of heaps. One is max heap and the other one is min heap. So now what is the difference between the max heap and the min heap? So now what is max heap and min heap? See, now let us analyze this particular tree. 75 which is greater than 55 and 40. That is parent is having the greater value than its two children. So here what we can say is each parent node is greater than its two child nodes. So see here, 55 is greater than 45 and 39. 40 is greater than 37 and 16. 10 is the 45 is greater than 10 and 19. So here a max heap is what? A max heap, every node, for every node I, the value of the child node is less than or equal to its parent node. Of course, except the root node. Why is that it is except to the root node? Because the root node is not going to have any parent, isn't it? So here we say that the value of the node is less than or equal to its parent node. But here we need to understand the root node is not having any parent. Or in simple way, we can also say like this, that every node is having the value greater than or equal to its descendant value. See here, the 75 descendant value is 55. So 75 is greater than 55. 55 descendant value is 45 or 39. So 45 and 39 are less than 55. Understood? So every node which is having the value greater than or equal to its descendant values. So this particular tree here, we can say that it is almost a complete binary tree because all the levels except the last level is completely filled. And in this last level, we need to be as left as possible. So here we are being as left as possible. So that's the reason we call this particular tree as an complete binary tree. Okay. So, and here if you see, this is the array representation of this particular tree. 75, 55, 40, 45, 39, 37, 16, 10, 9. So if we are going to write the index value, so this is 1, here it is 2, here it is 3, here it is 4, here 5, here 6, here 7, here 8, and here 9. So for I value is equal to, so now let us see what is the parent of 40. So what is the I value of 40? 3. So for my I is equal to 3. Let me check whether this condition is getting true or not. So here A of parent of 3. So A of parent of 3. Who is parent of 3? Parent of 3 is 1. 3's parent is 1. Okay. So A of 1. What is A of 1 value? A of 1 value is 75. So 75 greater than or equal to, what is A of I? I value is 3. So 75 greater than A of 3. What is A of 3 value? A of 3 value is 40. So this condition became true. Okay. So this condition is true. So this condition is true for all the values of I. It should be true for all the values of I. Of course, except the root, because the root node is not having any parent. So this is the max heap. In max heap, the root node will have the larger value of all the nodes in the tree. So if you can notice, in this particular tree, 75 is the largest of all the nodes in the tree. Similarly, if I am taking this particular tree, then 55 is largest of all the nodes in the tree. So here in max heap, the root node is going to hold the largest value of all the nodes in the tree. So here if you can check here, 75 is the biggest element in this array. That's why 75 is acting as a root node. 75 is the root because it is the largest. Now what about the min heap? Min heap is just opposite of max heap. That is, the parent node is less than or equal to its child node. So parent node is less than or equal to its child node. Parent node is less than or equal to its child node. Parent 19 is less than or equal to 40 and 39. 37 is less than or equal to 50 and 75. 10 is less than or equal to 16 and 19. So for any value of I, the value of the node is less than or equal to its child node. And in another way, we can say that for every node I, the value of the node is greater than or equal to its parent value or its parent node, vice versa. So here also, the root node is having any parent. So this particular condition is true for all the values of I except the root node. Fine. So here, if you can check which is the smallest element of all these elements, 10. So here, who is the root? Root will be the 10. So smallest of all the nodes will be the root in the min heap. And one thing, we are saying that less than or equal to, greater than or equal to. So what I mean by less than or equal to and greater than or equal to is we can allow the duplications. So in min heap, the root element is minimum of all the elements in the node. So 10 is the minimum of all the elements in this particular tree. Understood? So which is what we call it as an min heap. So what we have to do is, suppose let us think that I want to insert a new element. Now let us see how we can insert the data. Suppose I would like to insert the value 65. 65 node I would like to insert here into this particular tree. So suppose if you are trying to insert the 65. So 65 is less than 75. So it cannot be here. 65 is less than 55. So you can here insert here, or you can insert here. Say that 65 we have inserted here. So 65, when you insert, 40 has to come here, and when 40 comes here, it will 16 will come here. So now if we are inserting like this, it will not follow the complete binary tree concept. So we have to take care of that also. So while inserting, we have to see that it follows complete binary tree concept. So we cannot insert the node at the root, or we cannot insert the node from the root. We have to start inserting the node from the leaf node. So we should not try to compare this 65 from top. We have to insert this 65 at the leaf node. So it is very important that we have to insert the node, new node from the leaf node. So after inserting the new node at the leaf node, we have to check whether it is following the condition of max heap properly or not. Understood? So to satisfy the condition of the complete binary tree, we have to insert the node at the leaf, leaf at the same time as left as possible. So I cannot insert, so since I am saying that 65 we have to insert here, I cannot insert for this node or this node right node. I have to insert for this node left node. 39's left node I have to insert. So we can insert 65 here to the left of 39. And we cannot insert this particular 65 to the right of 39. Because it is going to violate the property of the complete binary tree. So is that we are inserting 65 as the left child of 39. So in array, see, of course, this is good, but whenever you are going to write any program or any algorithm or any code, no code or no program is going to draw images for you in the computer. Ultimately, what we are doing is we are storing it in the form of an array. So whenever I insert a new element 65, the 65 need to be inserted into this particular array with the index value 10. Of course, after inserting 65 here as the left child of 39, it is satisfying the property of the complete binary tree. But if you see clearly here, the 65 is not satisfying the property of the max heap, because 65 is greater than 39. So what we have to do? We have to compare this particular 65 with the 39. Okay, 39 is not greater than 65. So we have to swap these two things. So is that the 65 will come here and 39 is going to come here. So here we need to understand that we are not going to write these algorithms or code for drawing the trees. So for representing it, okay, but we write the code to place this 65 and 39 in correct positions in the array. So in program, how we can do that, or how we can do this? See, 65 is with index position 10. So take this 10 value as I value. Now what we have to do is we have to divide the I value by 2. So I by 2 is 10 by 2. 10 by 2 is 5. So here, since 10 by 2 value is 5, the 65 parent is at 5th position. So what is it? 39. So 39 is the parent of 65. Now 39 is clearly less than 65, which is not allowed here. So in array, what we need to do? We need to place 65 in this position and 39 in this particular position. So now here, 65 is here. It is not done even. We have to compare 65 with its parent. So what is the index of 65? It is 5. So my I value is 5. I by 2, 5 by 2 is 2.5. So the parent of 65 is at index 2 since we have to take the floor value. So what is the value of at index 2? It is 55. So 65 parent is 55. And clearly here 55 is the parent of 65 and 55 is less than 65. So 65 will come here and 55 need to come here. So my tree will be 65 here, 55 here. So that's the same thing. So I have to swap here. So my 65 will come here and 55 is going to come here. So in array, what we do is we place 65 in this particular position and 55 in this particular position. So now, so is that my tree is going to appear something like this. And even now it is not done. We have to compare this 65 with its parent. So what is the index of 65? It is 2. So my I value is 2. I by 2. 2 by 2 is 1. So in index 75, with index 1, 75 is there. So 75 is the parent of 65 and comparing 75 is greater than 65, the condition became true. Since 65 is clearly smaller than 75, so which satisfies the max heap condition. Okay, so now suppose think that I would like to insert with one more element, say 22. Whose index value is 11 in my array like this. And in the tree, I'll be placing this 11 value here, of course. Now what I have to do, when I insert this 22 here in the array, the value, index value of 22 is 11. That is my I value. So 11 by 2 is 5.5. Whose floor value is 5. So the parent of 22 is 55. And clearly 22 is smaller than 55. So there is no need of swapping. So this is a complete binary tree. At the same time, it is going to satisfy the property of the max heap. Understood? So that's all for now. If you like this video, please subscribe to my channel and press the bell icon for the latest notifications. Thank you. Thank you one and all.